Thank you so much for being here. This is the first episode, and we're a few minutes late. Yeah, we'll get into the habit. This is our very first time, so that's good. I'm Luca Antiga, CTO at Lightning AI, and my good friend Thomas Viehmann is here with me.
Hey everyone.
Nice. Okay. So we'll introduce ourselves a little bit, but what this is about is a conversation, a chat. The subtitle for this Thunder sessions is a chat about deep learning compilers and how the sausage is made. You know, AI is all the rage, and I'm sounding a bit old when I say that. Um, but you know, you use your chat GPTs, you use your Claudes, you recognize things through your cell phone, but how this is done and how the software that makes it work is written is probably something that is a deep learning framework somewhere that drives a model to go from a randomly initialized model to something that has actually learned what you wanted to make it learn. And this is done through deep learning frameworks. And as you know, running, but training even more, deep learning models is extremely expensive nowadays that deep learning models are huge. Thomas and I come from a time when fairly small models could be pretty impressive, right? Classify hot dog and not hot dog. Do you remember that?
Yeah.
Yeah, so it was pretty interesting times. But now, and so if you were a bit slower training that model, like no big deal. You spent a few hours on your home GPU doing that, like who cares? But nowadays, a run costs how much? I don't know,
I don't
at
know.
least a few thousand. Um, sorry, a few hundred thousands, up to the millions and so on. And you see crazy seed rounds and Series A, B rounds for companies training large models. So you want your thing to be fast. And so in this series, we'll meet regularly at this time. We want to see how we can dive a bit more in deep learning frameworks and what makes them fast, what really matters, and what is coming up on the horizon in terms of like what is a deep learning compiler, what does it do, and why it is important to even have a compiler. But let's not jump ahead and take a step back. So, Thomas, do you want to introduce yourself? Then I'll introduce myself a bit more, where we're coming from, and then we'll take it from there.
Well, yeah. Obviously, I've been like I jumped into PyTorch in 2017. So it's been 7 years, and along the way, I've seen it like in the beginning. It was like a very small thing, and then it became huge, and that is how I met Luca too, and eventually Luca and I wrote with Eli Stevens. We wrote the PyTorch book, Deep Learning with PyTorch with Manning, and a few years later yet, I had the pleasure of joining Lightning AI now to do Thunder with Luca, and obviously that's the thing that gives us the name here, and so yeah, that's me.
Yeah. So yeah, we go way back, right? It's 2024, 2017, and I remember back then that PyTorch seemed a very nice thing that happened because it was very painful to develop deep learning models up until that time, and PyTorch exactly captured the needs of researchers to iterate fast, easy debugging, and so on, even before performance was important. So
Yeah,
ergonomy, right? Yeah.
yeah. I mean, so before that, I played a bit with Theano and also TensorFlow in the early days. And so you basically wrote your program, And then it got compiled, and that took quite a while. And then you found that, well, at least I invariably found I had messed something up, and so it didn't work out. And then you had to kind of take the program apart again to get at the intermediate output. And then that was quite a hassle. And so I, coming from like a long time Python background, PyTorch felt immediately like NumPy, but with good GPU support, and so it was very natural. Had lots of missing features back then, so that was something to work on. And I remember, I think my first patch was with double backward for something, and so but what immediately clicked with me, and I think it's still true, that like PyTorch is a very neat way of actually coding up your models, right?
Yeah, exactly. Like I have a pencil, so this will be a very low slide draw plus code kind of thing that we want to do. And if you look at the PyTorch book, it's, it has a lot of doodles as well. So we like doodles in general. So what coding in a framework like TensorFlow one was, because then it adopted something that is more akin to a define by run thing. Yeah, we do a little bit of history, but because it's functional to where we want to go in the series, is in a TensorFlow program, you kind of define, do a linear, and then do a ReLU, and then do a linear. And this was the prescription of the program. Out of this in the back, there was basically an explicit graph being created, right? That was basically going to run in C++ under the hood, but the graph was already pre-created. So your Python program here was a specification for the graph. And so then you had a graph at that point, then would then be executed, right? And then maybe you did something wrong with the shapes, typically, as you do in deep learning. And then you would have you would get a long stack trace that would go into the guts of TensorFlow 1. And then you had to say, okay, what did you wrong here? If it broke here, maybe I did something wrong here. And then you had to iterate over this process, and it was painful. It was not immediate, right? What the novelty that PyTorch brought in is that you define a linear and a ReLU and a linear. And then if something broke here, the Python interpreter would actually step through this, apparently from a kind of UX perspective. You could put a breakpoint here and see what happened, right? Or you would just execute this one, and then once this one was executed, it would execute this one, which seems logical nowadays, but it wasn't the case before. And the reason why it was a graph was partly because you wanted to optimize here, you wanted to optimize the execution, but also because you needed to then compute the backward, right, of these operations. And so PyTorch made it possible to do that without building a graph, having what is called define by run. So the graph was defined while running, right?
Yeah, I mean, you're going back to Theano. Theano used to call the actual compiler the GCC, right? And so that was part of it. And PyTorch, basically, one part is that it replaced all the operations by something that are true library functions that actually do the thing. But then they also have the autograph tape, right? Which had been separate before, but it got put into the mix here to great benefit.
Yeah, to run even a bit backward, in the days when you were using Theano, I was using Torch 7. And Torch 7 was written in Lua, a programming language, actually Lua JIT, which was a great interpreter for the Lua programming language. And I liked it a lot because you could see through it. Like you could go from Lua into the C part. It was not C++, it was plain C, and then CUDA. Everything was very visible. I liked it a lot. But then it lacked Autograd. And so Twitter, I think, developed Autograd for Lua Torch. And so you could have the backward as a kind of an afterthought. But LuaJIT was actually already doing like what is called eager execution. So the Lua Torch would go through your linear, then your relu, and then your linear. So it would very easy to then debug what was going on. Typically you had to care about your backwards again if you didn't use the Twitter Autograd for Lua Torch. And then PyTorch basically replaced the Lua layer at the beginning with a Python layer, and then added Autograd, also taking the design for API design from other projects at the time that were experimenting with this, and that was PyTorch, and it felt so natural and great. So I want to start from here because the place we're at right now is that we have what is called PyTorch eager. And eager is also true for TensorFlow. At some point, TensorFlow 2 came in with eager mode, right? For TensorFlow, which was like similar, but not exactly the same under the hood.
I mean,
and then
obviously,
we have
lots of co-evolution going on here, right?
Of course. It's good that one framework has a good idea and then others kind of conform to it, because in the end, it's a UX problem. And we cannot, like we say it oftentimes, right, between us, like the UX part of it, it's so important because it makes people productive, and ultimately it gives them the ability to operate a different level of abstraction and also to make things fast as a result. So it's really important that the UX is something we all care about. So this is PyTorch eager. Eager because it executes each operation eagerly. And now we'll get a bit more in detail on what this means. And then recently, this is not the only compiler, but it was TorchScript before. But people know about Torch compiler, and we'll talk about JAX in a second as well. Where yes, you execute eagerly, but there's also a way to take these operations all together and do something with them so that you can optimize them together. So they're not eager anymore, but you have the opportunity to what is called fuse a bunch of them. If this is a possible fusion, there are many fusion, but you take things together and you execute them together. But in order to understand why this is important, we have to draw something. And maybe Thomas, you can comment on the CPU versus GPU. What happens when CUDA is involved?
Because I mean, if you look at it at a high level, you can imagine like you have the two processors, and for simplicity we just say two of them. So you have the CPU and the GPU, and they both, well, at first the CPU executes your Python program, right? And so the CPU, if you want, hits the linear layer you had just there, and then PyTorch will actually map that to a function called linear, and Luca here follows the convention that like the function is small linear, and this will actually instruct the GPU run a thing linear, run the linear kernel, as we call it, and so this will happen, and immediately after saying run this, it will take to the next instruction, and maybe a linear kernel also. Yeah, or a boxed linear.
Yeah, this is a linear kernel. Like it's a computation that goes on.
Right, and then comes the PyTorch relu instruction, and then this will also launch or queue, and then when the linear is done, it will launch the next thing. And this will be much faster because linear is actually a matrix multiplication, is a like an operation that is like n to the 1/2 in the matrix size, if you imagine square matrices, or if you like n3 if you count the dimensions. Wow. But so Relo is only element-wise, so it's n squared relative to that. So it's much faster than the linear. But so the queuing of the kernels essentially takes the same time, right? And now when the...
Sorry.
Yeah.
There's a problem with my abilities here. Sorry about that. No, I think it's actually the iPad thing that... Anyway, go ahead. I'll fix it.
And so when we reach the next linear in PyTorch and it wants to enqueue that, it could be that because Relo was so quick on our GPU, that actually the GPU had to wait for the instruction to run the next linear kernel. And so we have a gap in the computation there. And so one part is of the historical perspective is that, and then of course in your PyTorch program, there's a lot going on except sending commands to the GPU. Like you need to read data from disks or preferably SSDs, right? And so you have lots of things. And so back then, there was like a thing that kind of in the core loop, it worked. But nowadays, the GPUs have become, like the time the GPU spends have become much, much smaller. And by comparison, like the CPUs didn't get that much faster. And so what we have is that it's harder and harder to actually saturate a GPU, like give it all the work it can handle. And this is something I used to do consulting a lot, and obviously we did some projects together there too. And so one of the things is always like, if you want to like have your program go faster, check the GPU utilization. And if it's not close to 100%, you should ask yourself, like, not how do I get the GPU part faster, but how do I get like the GPU to be saturated? And so obviously compilers will only help you that much there. And basically it's something to see like where's my time spent, even just like writing down like which lines actually take the time. And I'm one of the people who always inserts just time it calls. But so finding out where the time is spent, that's the first step. And so one of the adages, if you want, is that Python is slow. But if you look at this here, yeah, there's the CPU that runs the Python, but there's other things going on here, like allocating tensor data structures and things like that. And usually the Python is slow is never your only problem, because like the Python overhead is of the same order of magnitude as the tensor allocation overhead. And so if Python is slow is the problem is also like the tensor framework overhead is also slow. And so here, if we can reduce like the number of things that are going on the CPU, we're always in good shape. And so one of the reasons why we want to have kernels like combined is to have less things going on the CPU.
Yeah, great. So that was a lot of information. And in fact, it's all there is when we are thinking about why, or not everything, if you then go distributed, but a lot of what there is when we talk about the importance of compilers. And the eventual things that even a framework like PyTorch Eager needs to do in order to minimize the fragmentation, right? So one thing is the selection of kernels, but the other thing is, for example, attention. If you look into attention for models, like you look in our LibGPT or in NanoGPT or many others, you have a particular call for attention, like SDPA.
Scalar.product attention.
Product attention, exactly. So the scalar.product attention kernel exists because there is a fused kernel that performs the whole attention dance. But it's not that you cannot write it out manually. And there are other considerations about like flash attention and so on. But ultimately, the fact that you can just select one single kernel that performs all the attention computation is advantageous also because otherwise it would be fragmented in many operations. It will be not only wasteful from the standpoint of like launching multiple kernels, but also of the fact that you need to somehow materialize a lot of information in between the kernels so that you can pass them from one to the other.
I mean, that is like the next step is what's going on inside a kernel, and that's like basically you have memory loading and loading things from, and GPU memory these days is a lot faster than it used to be. But so you have, just like you would have on the CPU, you have like loading things from memory that takes time. And then computing things also takes time, right? Because it's actual effort. But so this transfer is one of the things that really takes a lot of time. And if you've like watched the CUDA mode sessions, we've like nerded out about that a whole lot. And if you want to get into the full details, I encourage you to watch that. But so basically, if you can avoid writing stuff to GPU memory just to read it back, and here it would be like the attention matrix that covers like which tokens is influenced by which input tokens, like which output is influenced by which output. If you manage to avoid like writing that into memory, it will save the memory, but it will also like save a whole lot of time writing things to memory. And we saw that relatively early on back in the day with LSTMs, which had like a lot of pointwise operations. You multiply, you take a 10H, you add stuff, you multiply again. And all these things in traditional eager PyTorch that would write into the GPU memory and then load it back in the next thing. And by just eliminating this, because all the individual operations were like tiny, you could speed it up by a whole lot. And that was actually why the first TorchScript fuser came into place. And with that, we managed to like get back into the neighborhood of like what cuDNN did for LSTM, but with plain PyTorch code. And so this is the thing about like the specialized attention kernel. Yes, it's cool that we have that, and it's a lot faster. And one part of it is that it avoids like creating a huge tensor in memory. But the other thing is, of course, if for everything we need to write a new kernel, that's like slow. So at some point we need to generate kernels, right?
Exactly. So, and we're getting into the whys of compilers now, because if this takes a lot of time, and this thing, we need to avoid it, but we have the convenience of an eager framework to develop things so that we can do define by run, then there's a tension here, because we would like to say, okay, I have a program that calls a linear ReLU or a matmul addition, whatever, and I want to be able to step through it without me having to think about the fact that there's another basically language on the other side, and that errors messages and profiling, whatever, I need to operate at that level, which is even a bigger tension. But if we want to make this actually efficient, we need a way to acquire this, to know exactly what the whole computation will be, and then to kind of process it so that I can put things together and reason about them so I don't have to do this dance here.
Right.
And this is everything, like, this is what a compiler is about. Then we can think about like other things that compilers do. Like, for example, they could make things distributed, or they could transform programs in a way that is not exactly what we're talking about right now. And we'll get into that as part of Thunder. And of course, Thunder is not, for sure, it's not the only compiler there is. In fact, Thunder is very young, and you can even argue that it's fully there. It's not fully there yet. But we would like to build it in the open and start reasoning about it because it's already very useful for a few things. So that's why we're here, and we want to socialize ideas in this area. But let's recap a bit what we have said so far, because we've said a lot of things. One is, we have the history of PyTorch TensorFlow, PyTorch defined by run, and then being able to spell out the model just with commands, like just as if it were NumPy. But that means that every single command, like every single line of code in PyTorch, will launch when you run it on the GPU, will launch a kernel. And the kernel will take some time, to be set up, to be launched, for data structure to happen on the GPU, and then to run. And this is not like the find by run is only elusively going sequentially, because if you have 3 operations and they're all on the GPU, they won't run at the same time as your line Python interpreter steps through the program, which we can see here at the top. But they will schedule things to run on the GPU. And so as I tell my Python interpreter, now run on linear, there will be a bunch of things that are scheduled on the GPU to eventually run as soon as possible on the GPU. They will run on the GPU until it's done. And then the GPU will say, okay, what's next for me? It won't wait for the GPU to tell it what to do. It will look at its own internal queue of operation to see what's next. And what's next, if the CPU in the meantime scheduled a ReLU there, it will launch a ReLU kernel. It will set things up and launch a ReLU kernel for execution. If nobody schedules anything on it, then we're in the situation where we're just waiting, and the GPU will be waiting until somebody schedules things. And this is also goes back to where you need to benchmark something on the GPU. You need to call it CUDA synchronize, because your CPU program might have said, yep, I'm done. No, you're not done. See, GPU is still running until you call CUDA dot synchronize. And this will guarantee that this line of code will block until this time, right?
Right.
At which time you can time things, right? So this is also why it's tricky to properly benchmark things on the GPU if you don't know how things work under the hood. Great. So this is how PyTorch Eager works. And now, but for example, this is not how JAX works or Torch Compile works, because frameworks like JAX or PyTorch plus Torch Compile or PyTorch plus XL8, PyTorch XL8 or Thunder acquire the program. So from a discrete representation of the program, they put it together in something that is a description of the program that kind of looks like a bit like what TensorFlow had back then, but it's not. You as a human, you're not required to be a human compiler. It will generate a trace of computations or a graph of computations, whatever, or a function that represents the computation. That then can be translated into something else. And that something else is a program that is a lot more compact, and where operations that make sense to do together, they're done together in a single kernel. So you can have a sequence of these little things. But now you can, if I have this, followed by that, I can now replace it with something that looks like this.
Yeah. And to put this into perspective, like cuDNN had a linear with a activation fuse to it, like for a long time. or kublas. We had that, but we couldn't really use it in PyTorch comfortably because it would need us to rewrite our programs. And so this is where the compilers come in, and they will like look at several instructions at once, and then have opportunities to actually say, yeah, I know a kernel for that, and dispatch to Kudian, and like Thunder doesn't have a lot of its own kernels, but rather it like orchestrates them and dispatches to various ones. But so Torch compile or JAX through XLA, they will actually like build kernels, right?
Yeah. And another area where compilers are actually quite interesting is the area of distributed, because now we know, we're not just talking about one single GPU doing the work, right? We're actually saying, okay, now there are multiple of them doing the work, but while doing the work. And why multiple of them? Well, because you need to go through 3 trillion tokens. So you kind of say, okay, you will take a chunk of those called shard, and you take another chunk of the data, but also because models are so large, they don't fit a single accelerator. Right. And so you need to take, okay, each one of them, one GPU will take just a part of the model, for example, in different shapes and forms, and we'll get more into this. From a representation of your program that is like, again, operation by operation, and it's expressed to run on a single machine, you now need to get to something with or without a compiler that can be actually broken up to multiple machines, right?
Yeah, and I think that's kind of one of the key things you say here, with or without a compiler. So in a way, you could say, well, yeah, the left thing on the single GPU, that's one thing, and the distributed is a completely different program. And of course, that's a fair point. And until you have something that says, no, I can go from one to the other automatically, basically you have to do it by hand. But imagine how much nicer it would be like if you didn't have to.
Yeah, for sure. But one may argue, yeah, but with FSTP, for example, you can do it without changing your program. Right. So that is true. But also, if you look into FSTP, and we'll get into FSTP, but it's one way of sharding your model and distributing it. It needs to look into the program and also have heuristics of what happened and what will happen in terms of memory allocations. So in a way, it's trying to get a global view of the program while being eager in its PyTorch implementation. It's still kind of eager. And it has added heuristics to be able to reason about the program as a whole. For example, one of the things that you have in FSTP is the ability to overlap computation and communication. Whoops.
Yeah, and that will essentially like give you a picture very similar to the CPU and GPU one, except now you have like time spent waiting on the wire where potentially both the CPU and the GPU are idle, right? Or it like is allotted to the CPU time. But yeah, so essentially you always have the timelines and you ask yourself, well, yeah, can I get 100% utilization there? And so that is one of those things that we want to get to, right?
Exactly. So computation and communication, like in a naive world, you do your computation in different GPUs, and then you spend some time to do communication. Some distributed strategies like FSTP give you the ability to kind of like fudge with this and say, okay, while you're computing something on one linear, now I'm going to communicate. I'm going to spend the time in parallel. So the CPU is going to spend time to do the communication part. So when it's time to execute the next thing, I've already communicated what I needed to communicate. So you don't have this, or you try to minimize the idle time.
Right.
And this is very important. This is much less easy to do, of course, with things like tensor parallelism, because of various issues. We will we'll get a bit into that. But this is also something that benefits. What I wanted to say is that this is also something that benefits from the understanding of the program, from a very granular instruction by instruction thing to a more global representation. So you can then decide how you can distribute the program. Because now you will say, okay, in 3 instructions, I will have to do a linear. So let me, right now, put my communication there so that I know I'm running ahead of time and I'll know what I will be doing.
Right.
Yeah. Okay, so maybe that's a good time to dig a bit more and say, okay, what happens now if we use Thunder, which is a compiler we're working on, to have an idea on how representation is computed. And just have a quick a sneak peek of that, and then we'll get more into it in the next few episodes. But do you want to share your screen, Thomas?
Yeah, if you unshare yours.
Of course.
Yes, so let me share like a Lightning Studio. Obviously, we like to run it on studios.
Well, yeah.
And so the first thing we need here is, of course, get Thunder. I encourage you to check out the 0 to Thunder Studio, because that's like, it has your everything installed for you. But if you have to do it manually, you can just, if you can type in the URL, you can.
Yeah, this is where you find Thunder. You're more than welcome to check in the repo. You can see .git.
My Git food doesn't involve clone. Okay, so you have Lightning Thunder, and of course you can just pip install that. Or I like to, because I'm that kind of person. I like to set it up with develop, which will of course register it into the Python. And then one thing that is good, and we have the install instructions. One thing that you typically want to have is from our friends at NVIDIA, the NVIDIA Fuser. And so this will come from a package, and I have to look up the installation command all the time too. So it's nvfuser.
Yeah, while you're typing, the Fuser is exactly something that takes multiple operations and produces a CUDA kernel, which is the program that runs on the GPU, that does them all together. So you don't have to do them piecemeal. And an example of another Fuser is Inductor, which is within Torch compile, does the same thing. So it takes a number of Torch operations and generates a bespoke kernel for those just in time that is optimized for what you want to do.
Right. And while we're waiting, we can write our little MLP here. So import Torch, import Thunder. Yeah, that already works, right? No. Oh,
Triton.
Triton. Oh, it will reinstall Torch here.
Oh yeah.
Just uninstall Torch. Yeah, so
so you need to restart your kernel as soon as it's done. Yeah, okay, that's fine. Torch Vision, we love Torch Vision, but it's not relevant right now.
Okay, so let's restart here. That's with the live coding.
Yeah.
Okay, so
yeah, but we like
let's try it again.
Adventurous.
And I will switch to the larger layout now. Did it Yeah, now it ran.
Yeah, we can probably also
And so-
close the terminal.
And so we can have a model that is like a little MLP, and hopefully my PyTorch foo is still good enough for that. So we have a hidden layer, and this could be, I don't know, 128 to 512. And then our favorite, and I should not save that much space, right? And then you have your favorite activation function. Obviously, Gello is now all the rage, right? And how is that spelled actually? Is that right?
Let me look it up.
And then you have torch and then linear, and that goes from 512 and say 2 if you have some
Yellow is all
classification
capital
thing.
with the E, capital E.
Oh yeah. Okay, so that worked. I have this little model, and can I close this now? Okay. And I can like make a Thunder module out of it just by saying thunder.zip and then my model, and then I can run it with some input, and this is not very deep now. Random batch size of 16 and 128 inputs. And so this ran, computed some output. But now what we can see, Luca promised you that we would have a representation. And so with Thunder last traces, we can actually take a peek. And this will be the last thing that ran. And I'll just
Traces.
show you like one of the last traces, and we'll talk about this. Oh, last traces. And this will give you many of them, and we'll tell you why in a bit. And what you see here is that it went through the program, and now we have actually a function here that has our input, but it also has the parameters of the neural network as inputs. And so it has the first linear, it has the Gello, and we can actually see how the Gello is decomposed here already. And then we have, and then we have the second linear, and this is returned. And so you can see here the program that we have, and obviously this looks like a Python program, a Python function. That actually is a Python function, and you can actually run it if you want to. And
Yeah, so
this is
just
our
to,
representation of this program, right?
Exactly. So from if you scroll up from the beginning, from our little program representation, that was an eager representation of, that was more of a declaration of our program, but it was a program that could run eagerly. So if you step through it, you would see that you would stop at linear and then Gelu and then linear, and this will launch an individual kernel, CUDA kernel, one or more, because you're not guaranteed that one instruction is one kernel. Some torch functions may launch a different amount of kernels depending on many factors.
Right.
Usually it does the right thing, but it does it discretely. So what we did is we tried to acquire this program and say, okay, if I need to break down this program into little pieces that are the constituents of this computation, like the fundamental pieces of this computation, then when we have those pieces and we have the list of them, we can also reason about what to fuse, what to put together, and whatnot. So the very first thing that a compiler needs to do, but also a good way to look into what actually happens under the hood and how the sausage is made, is take a program, go through the JIT, and print the trace. And the trace is a sequential representation of your program. And here we can see what the inputs were, but we can see the first linear layer, which has been turned into a a function, because functions are a good representation of a running program, because everything is there. There's no hidden state anywhere. So all the inputs that go into the function are actually inputs to the function, and there are no like, oh yes, but this object has some parameter that it's storing somewhere, and you don't have visibility on it because we wouldn't be able to work with it very well. So that's the first linear, and then the GELU. So the GELU, we also decomposed it and broke it down into what we call primitives. So what the GELU is that division, and then the error function, and then the multiplication. You can look it up on the Torch documentation, but actually these are all the operations that go on in GELU. And so if you have then these primitives, and you have the ability to say, okay, let me put these primitives into a kernel that is optimized to execute them together, or if you have directly a kernel for GELU directly, right? Both ways you can choose your adventure here to stay high level, to stay on the primitives, and Thunder allows you to do that. Then you can take this together with the previous linear, and if it's convenient, and if you have the capability of doing so, you can put them all together in a kernel. That's the first use of this. Maybe we can also show the CUDA stuff then that is generated from here.
This now actually was not with CUDA.
Oh, okay. Sorry about that.
And
or maybe we can do it the next time. So
yeah, let's do it the next time. I think we should have that as a cliffhanger. So how we get back to the kernels, that will be next time.
Yeah, absolutely. Okay, great. So anyway, I'm happy to conclude this first episode. It's a pilot, right? No, it's more than a pilot. It's one thing that will happen next week again. Thanks everyone. I invite anyone that watches this to post comments. Be nice in general, not just in the comments. Like, that's a general thing. It's a good thing to be nice, and it lets you focus on the things that matter.
If you have one take-home message, be nice.
Yeah, and yeah, we'll get into this step by step, and we'll get into a lot more depth in the next episodes. If you didn't understand something, leave a comment. We can point you to things, or you can help out having us produce content that will cover the doubts and so on. So hope you enjoyed it. I had a lot of fun. I hope Thomas was the same.
Yeah, same here, Luca.
Okay, great.
See you next time.
Thank you.